solution of different species. And one of the things was we were talking about a reaction like this where we have iron 3 plus an electron in equilibrium with a reaction that goes to iron 2 plus. So there we go. Good. And now remember we talked about when we put a platinum electrode in that particular solution, there will be an equilibration between the energy of the electrons in the iron 3 plus and 2 plus with the energy of the electrons that are in the platinum metal. And so once that equilibrium is made, no current will flow at that point, and we will have the same potential of the solution as of the platinum electrode. And so that is an equilibrium point. Now what happens though if we take, again we're going to draw a diagram of potential, where potential versus current, where current is up in that axis, potential is this way. And notice also we're going to do the convention of having potential increasing more negative to the right. And that's kind of an odd convention for electrochemistry, but that's the way it goes. So we know that this particular reaction has an equilibrium potential of plus 0.77 volts. And we discussed a little bit last time about having that versus the normal hydrogen electrode. And we'll talk more about what we mean by that later. But remember, we always have to measure things versus a standard material. So that would be right around here someplace on that diagram. Now what happens if we try to force that reaction away from its equilibrium point? Well, what's going to happen in this particular case, since we have a redox couple, we can actually force the reaction away from equilibrium by applying a more negative potential or by applying a more positive potential. In that case, because the system is no longer at equilibrium, we have a process that can allow current to flow. Now, that doesn't mean it will flow, but in fact it can flow. And so in this case, we do see a current flowing. Now, but let's go back to the idea of things being at equilibrium. If something is equilibrium, remember the thermodynamic idea that something at equilibrium is that we can change the potential or the direction of a reaction by infinitesimally small amounts of potential. So if we change the direction of the reaction by applying a very tiny negative potential or applying a very tiny positive potential, we can change that potential direction. So there's actually a description of that. We use the free energy, and it turns out that we can write an equation for the change in the free energy at equilibrium as a potential of this electrochemical potential, which we'll call E0. And there is an electrical term here, NF, which N is the number of electrons, and F is the Faraday. And we'll talk more about what those constants mean later. But for now, recall that there is an agreement between the thermodynamic values and this electrical value, the E0. Notice the delta G value. Now remember delta G from chemistry. Delta G was an indication of a spontaneity of the reaction. If we had a negative delta G value, that meant that the reaction was spontaneous and would occur. And so delta G is a reaction direction process. Delta G is positive, that reaction was considered to be non-spontaneous and would not occur. However, and so we can think of positive potential values as also being spontaneous reaction processes. We have a positive electrode potential, that should be a spontaneous reaction because of the coupling between delta G and E0. But on the other hand, there is really no preferred direction for writing a potential down. If we take a battery and we measure the potential of our battery, one side of the electrode might be considered to be positive if we use a voltmeter, and one side of the battery might be considered to be negative. Which is which? I mean, it really depends on how we put the voltmeter leads across the battery. In one case, we might measure a positive voltage across that battery, but if we switch the voltmeter leads to the other direction, now we have a negative potential across that battery. So potentials are not signed ultimately. They're not having a signed value to them. They're actually just differences. And like any differences, it depends on our choice of reference points, whether they're positive or negative values. It's like saying, what's the elevation of this room? Well, it depends on our choice of reference values. If we choose sea level, then we have a positive elevation. If we choose the orbit of the moon, then we have a very negative elevation. So again, those choices of potential differences are not fundamental. However, our thermodynamics require a negative or positive value to indicate the spontaneity of the reaction. The way we get around that is we come up with a term we call the EMF, which stands for electromotive force. And the electromotive force is a signed potential that's signed in the appropriate way to correlate to delta G's being positive or negative. And so it's a convention. It's not a function, that's not a part of nature, it's actually just a human convention whether we call something being positive or negative. So for example, our reaction of iron 3 plus an electron in equilibrium with iron 2 plus has a EMF of plus 0.77 volts when we draw it in this direction, but if we write the reaction in this direction, instead of a reduction, we write it as an oxidation where an electron becomes removed from the system. Then we have an EMF of minus 0.77 volts. So EMF is this sign potential that reflects the direction of the reaction from either a spontaneous or non-spontaneous process. Let's just do an example. Suppose we have a reaction where we have a cell written like so, where we have a tin electrode in contact with a tin solution of 1 molar. Then again we have a porous separator, and we have iron 3 plus 1 molar and iron 2 plus 1 molar, and then we have a platinum electrode. Now if we measure the potential across this cell, in other words, we hook a voltmeter leads up to the platinum and tin electrodes, and we can measure a potential of plus 0.906. All right, what's that mean? Well, that means, according to that, because of the convention we've got, that means that the reaction is spontaneous in the direction we've written it. And it's spontaneous in the assumption that this is the anode and this is the cathode. Can we see all that? Okay, good. Now, if we wrote the reaction the opposite way, the same exact set of chemical systems, but we switched the voltmeters or leads around, and we would get a negative 0.906. But as long as we assume that the tin is the anode and the platinum is the cathode, and we measure the potential of the cathode with respect to the anode, then we get a positive value there, and that indicates a spontaneous reaction. What's that mean? Well, that means that the net reaction is the tin being oxidized and the iron 3 plus being reduced to iron 2 plus. So when we write these cells, we always try to write the anode to the left. If we write the anode to the left and we measure the voltage so that that is the negative voltmeter lead, and whenever we see a positive cell potential, that's a spontaneous cell reaction. Okay, so how do we calculate what that cell reaction is? Well, we can look up in the table in the back of the book or in the library. You can find a lot of these tables. You can see that the cell reaction, half cell reaction for this particular cell is 0.77 volts for the reduction of iron 3 plus, and if we look in the back of the book, we'll see that tin 2 plus, written as a reduction going to tin metal, is minus 0.136 volts. in the back of the book. Now, if you look in the back of the book, you'll notice all these half-cell reactions are given as reductions. Well, we know that this reaction actually has to be an oxidation, so we actually have to write it like so. Tin going, I can't write today, tin going to tin 2 plus 2 electrons. And so in that case, the electromotive force now becomes a positive value, 0.136 volts. So we can add together these two reactions and these two values, and we see that our net reaction now is 0.906 volts, and it's a net process of 2 iron 3+ species reacting with tin metal, going to iron 2+, I'm sorry, iron 2 iron 2+ plus tin 2+. And we had to multiply the top reaction by 2 so that the electrons all canceled out. We never have a net reaction with electrons floating around in the system. So this reaction, because it has a positive cell potential, is a spontaneous reaction. And that would happen. If we took tin metal and we mixed it with iron 3 solution, we would see the tin being dissolved and the iron 3 being reduced to iron 2+.
And we have to multiply the reaction for times 2
right.
to cancel the electric, but the potentials were not multiplied when we added.
That's right. That's a good question. He's asking if, since I multiplied this by 2, why don't I multiply the potential by 2? Well, the potential does not depend on the amount of substance that we're using in the system. For example, if we have an A battery or a AA battery and a D battery, there's the same chemistry, but they have the same potential. So that's an example where we don't make any difference. So if I have twice as much iron 3+, it doesn't make the potential twice as large. So we don't have to worry about that. So this potential does not change in that case. So this reaction is spontaneous. In fact, the only reason it doesn't automatically occur is because the voltmeter doesn't allow current to flow through it. Now, if we just took the wire up to this system, current would flow rapidly through that system, and we would get the reaction as shown, occurring at those 2 different electrodes. Also, if we took a voltage source and we applied an opposing voltage across the system, we would cancel out. We could cancel out that 0.906 volts and make that reaction not occur as well. All right, as you can see from your notes.